Good afternoon, everybody. Many thanks for taking time to join us for today's Tech Talk. Today's Tech Talk is on column strengthening. I'm Steve Musa, one of the operations team. Tech Talk is technical. It's going to be done by my colleague, our technical director, Jayesh. Good afternoon, Jayesh.
Good afternoon, everyone.
So first thing I'd like to do is just run through the objectives of today's Tech Talk. We look at why would you use carbon fibre, what would you look at to choose to use this as a solution. We'll be looking at column strengthening in depth. We've got some really good projects for you to look at. And then any questions at the end of the Tech Talk, if you want to ask us a question, you can drop us a line. So let's jump straight into it, Jay. Why use carbon fibre? What is the reason people would use this as opposed to traditional methods, concrete and steel?
Yeah, so carbon fibre strengthening becoming quite popular these days. The reason for that is that this is very high strength and lightweight material. So just to give you a feel in terms of number, carbon fibre is at least 3 to 4 times stronger than steel, at least 7 to 8 times lighter than steel. So you could see strength to weight ratio and why people prefer to use FRP over traditional methods. It is used as an external reinforcement, so you apply FRP from the outside of a structure. So that's why it is called externally bonded reinforcement, or it comes under the EPR technique. We can strengthen concrete, steel, wrought iron, cast iron, even in timber structures. So you can do pretty much all type of structural construction material strengthening using carbon fibre. And for that reason, it is becoming quite popular because it's much quicker to apply as compared to the traditional method of concrete and steel.
And a lot of people think it's a new technology, which isn't really the case now.
No, that's a misconception. But as compared to concrete and steel, FRP, you can still call it as a new technology because concrete and steel has been in the industry for over 100 years. Carbon fiber was first used in 1944 in aerospace engineering. Then they started making all the aeroplanes, fiber boats, motor cars using FRP. And then in 1988, this was first used in construction. So it is 37 years old technique, but it's still comparatively new than concrete and steel, but we can't call it as a new technology because we have more than 30 years of case study available.
And generally speaking, the clients or the people that we would work for are structural engineers, but we're seeing a big uptake in main contractors are coming to us through structural engineers now because it's quite an economical solution.
It is, yeah. So generally, if you see the whole cost of applying carbon fiber, using carbon fiber strengthening, and if you see the cost in terms of material, labor, disruption to your structure, and most importantly, time in doing that strengthening, then this is the most economical solution. So generally what happens is that people only see the material cost of carbon fiber and compare it with like for like steel or concrete, and they sometimes find it expensive. But in reality, it's not just the cost of material you need to look at. You need to also look into the cost of applying that material into the position and the place and all those things. And that's where we actually save the money. The carbon fiber is very low profile material. So the typical thickness of one layer of carbon fiber is around 1 millimeter. So imagine if you're able to strengthen a beam, column or a slab with one layer, it means you're increasing its dimension by 1 millimeter. And because it is very thin or low profile material, it's much lighter in terms of weight, so very easy to apply in place. So you save a lot of time because you don't need cranes to put it in place or wagons to carry it from one place to another place. So for that reason, there is a lot of time saving in carbon fiber, and that reason architects also prefer to use it because they like the shape of the structure they've got rather than putting another steel section and changing it completely.
Okay. So we're going to look at some of the projects that we've worked on quite recently, specifically obviously with column strengthening.
Yeah, so we'll talk about the column strengthening concept first, technically, how it works and how we do column strengthening with carbon fiber. So generally, column strengthening is done for improving the axial load capacity. Now, if some of you have watched our previous Tech Talks, you may have noticed that I said that carbon fiber is very good property in tension. It is always recommended to be applied onto the tensile face of structure. It's not recommended to improve the compressive resistance of the element and all those things. But in this instance, or especially in cases of column, even though it's a compression member, carbon fiber still works in tension. The reason is that here we work on confinement theory. So what we are doing is that we are confining the concrete with a much stronger material from the outside. That's why circular is the best shape to strengthen, because what happens is that when the load comes on top of the circular column, it will start to dilate, and FRP provides resistance through the dilation. Now, because the stresses are even throughout the perimeter of the column, the whole of the FRP becomes effective at once. That's why we get a lot of increase in circular columns. The same confinement theory we can use on square and rectangular columns, but there are two things we need to make sure. First, these corners on all of these square and rectangular columns, they need to be rounded off to a minimum radius of 20 millimeter.
Okay.
And that's not just an application requirement, it's a design requirement as well. So the formula is given in TR55, has an expression of RC, which is radius of curvature. We need to use that as minimum 20 millimeter. And the second thing we need to note is that the aspect ratio of the column, especially in rectangular columns. So we can work on confinement theory and rely on it up to an aspect ratio of 2. But if the aspect ratio is more than 2, then technically we should do combined axial and bending analysis and see whether we need any longitudinal FRP or not to improve the moment resistance of the columns. But generally, confinement theory works on pretty much most of the columns.
Okay.
Now this is the axial and bending curve for the columns, which we called basically interaction diagram. So this basically works for rectangular columns or higher aspect ratio columns. So what we are trying to explain here is that we can still work on confinement theory using this method. So what we do is that basically whenever an structural engineer is assessing their columns or existing columns in a structure, they can just change the concrete strength in that column, because what happens is that when you change the concrete strength, this curve will shift outwards. So probably your axial and bending loads will come into the curves. So we can work on that theory and still confine the column, even if they are higher aspect ratio columns or something. But the increase in them is very limited. So that's the reason that we have to do combined axial and bending analysis and see whether we need any longitudinal FRP or not. But as I said, in most instances, we are able to justify it with just confinement theory. But then we also move on to the blade kind of column, where we have the aspect ratio of around 3 to 4. So even if our confinement theory is showing that the confinement will increase the concrete strength and it will be sufficient for axial and bending onto that particular column, but even in that as well, because it is you've got a much longer edge on one side, the confinement will not be fully effective throughout the perimeter of the column. So in those instances, there is another technique which we can use, which is we used it, or we figured it out by doing a lot of research and development with universities. So we work with many universities around the world, and they do different types of research. So one of these universities in Greece did this kind of research, where they checked these higher aspect ratio columns, where aspect ratio is around 3 to 4 with the confinement, and they checked how much effective carbon fiber will be, and they figured out that just confinement itself will not increase the strength significantly, because as soon as the stress concentration becomes onto the corners fail first, and your confinement in the middle doesn't work. So the solution to that is using some carbon fiber anchors. So this is shown in the image there. So we could see if we don't have these anchors, we have a full stress concentration in the corners. Your corners will push out first, and your confinement in the middle will not be effective. So what we can do, we can use the carbon fiber anchors, either one anchor in the middle if this on the smaller size, and the two in the longer edge kind of thing. So what it makes is it becomes like a small kind of column. So here now the confinement becomes fully effective because you've got these anchors. So as soon as your corners will try to push out, these anchors become active, and they become as a tie. So they will stop the FRP to push out. And that's how the confinement works much better in these instances. So this is the way we can do higher aspect ratio strengthening. So we can apply the FRP as standard confinement, but we have to use these through anchors as a tie, so that the confinement between at the longer edge will remain effective throughout.
These specifically that you've been talking about, the types of anchors that we design to use on these types of projects?
Yeah, so generally these anchors are used on all types of strengthening, so whether it's beam strengthening, slab strengthening, or column strengthening. So there are two types of anchors we have. One is nominal anchors, which are smaller anchors, which are generally used for construction detailing. So where we are, stopping the FRP just to provide an end detail or something, we'll use these nominal anchors.
And that's a small schematic on the right, yeah?
Yeah, small one. So how it works is that we drill a hole into the concrete, we saturate the anchor, put half of that anchor into that drilled hole, which is filled with epoxy, put, display the remaining half onto the face of the concrete, and then put one more layer on top of it. So now this will become one unit which will cure simultaneously, but it is actually going into concrete, so it provides you additional anchorage or bond capacity. So debonding or delamination failure will not happen. So that's how these nominal anchors are used, which are mainly to provide further assurance against the debonding and delamination failure. Then we have these bigger anchors, which you could see the guy holding in the hand in the middle image. So they are called super anchors. So they're specially designed anchors which are designed for a particular force.
Yeah.
So these are the anchors which are used in the column testing as well. So how these anchors are worked, so whenever we are designing carbon fiber, we know the force in the FRP in that particular location, and if there is an obstruction in the way, we can use these anchors to transfer strengthening from one side to another side. So the same thing we did in the column as well. We knew the push out or force in terms of the load and everything. So that force we wanted the anchor to resist, and that's how these anchors were designed. So again, there are some images shown which are not from the column but from the slab strengthening and wall strengthening environment. So you could see there is a slab strengthening example where we drilled a hole through the column, passed that longer anchors through, splay them on both sides and put one more layer on top of it. So these anchors become as a tie which is transferring from one side to another side. That's how these anchors are used. So they'll be specially designed by us for a particular force.
Okay. So we're going to have a look at some specific projects where we've used all the systems that you've been speaking about. Yeah,
so we'll talk about a couple of projects. So this is like in a building environment from London. It's Laser House in London. It's following the same theme which is happening a lot these days, especially in central London area. They've got an existing structure, they want to improve it, want to add additional story on top of it. The same thing was happening as we could see in the 3D image at the bottom. So they added additional story on top of it, and the columns in the basement got overstressed. For that they needed strengthening. Now the solution engineer proposed was, first of all, just to highlight, these columns are not our normal reinforced concrete columns. They are steel columns encased in concrete.
Okay.
So the solution proposed by engineer was that, take this encasement off, weld another plate onto the flanges of the column, and then recast this encasement. Now in doing that, first of all, it's a very destructive way to strengthen the structure. It will take a lot of time, temporary works and all those things. And also the number of columns needed strengthening was around 80.
Yeah.
So if you do that on 80 columns, your program will be significant. So they approached us, and when we were checking these columns, we found that there is some longitudinal and longitudinal reinforcement in this encasement. So longitudinal reinforcement along with the links. Now, if you have that kind of reinforcement, then there is a clause in Eurocode too that you can treat this column as composite column if you have the minimum reinforcement and concrete strength. So once that was done, the column needed strengthening gone down from 80 to 20.
Okay.
And only 20 columns needed strengthening because the strength of the concrete in this encasement was less than 20 MPa, which is the requirement from the Eurocode clause. So our design goal was very simple. We had to confine these columns with carbon fiber so that the strength becomes 20 MPa or more. So only 2 layers of carbon fiber needed there, and it was done in a much quicker way as compared to the previous solution they proposed. So that's how the strengthening was done using carbon fiber, and again we saved a lot of time and money for the client, and ultimately the question why contractor preferred to use carbon fiber, purely because of the time and program.
The time that was saved and the money obviously saved on program, yeah. This is a really great example of where you can save a lot of time on a project we completed last year.
Yeah, so this is a new build structure. It's Damak Tower in 9 Elms. So this is, again, in this instance, the strengthening requirement is not because this design is incorrect or the construction is incorrect and all those. It is just the strengthening was needed because the plans were changed in the very end. The client wanted to use something else instead of what it was designed for. So generally there are, what it's happening there is that there are 2 tower blocks, as you could see in the first image on the left hand side. So one in the front and one at the back. These tower blocks were supposed to have a link bridge between them. That link bridge was going to be a precast concrete link bridge, which had no connection with these structures. It was independent structure. But in the end, client changed their mind and they wanted a steel bridge instead, because that was quicker to put in place and everything. And that steel bridge needed a connection with these columns. Now this column is already very heavily loaded, and also it is not designed to take that kind of lateral force. So you can't, put another plate and connect a bridge with it. So it needed strengthening, and the client asked their on-site contractor to cast another concrete jacket around it. The contractor said it can be done, but it will take at least 2 weeks to do that work. And after that, they have to wait for 28 days for it to cure before they can connect the plate. They did not have that much time because the bridge was already ordered, it was in transit. And as you could see in the leftmost image, there is underground station nearby, so there is no way we can store the bridge on site. So they had to do strengthening in a much quicker way. So they approached us, we checked the feasibility. It was feasible to strengthen the column. They liked the proposal and everything. So they given us the order. We started work on Friday evening, finished it by Monday morning, and the following weekend they were able to connect the plate. So purely because of the time, carbon fiber was the much better option.
A great example, as we've said previously, for the design and specifically for the main contractor to look at this solution purely on time saving.
Exactly, a time savings. Also from architect's point of view, if you see if they would have gone with concrete jacket solution, it would have changed the shape of this column significantly. So all the columns would have become disproportionate in terms of size, and the facade panels would require changing and all those things. But with carbon fiber, it was not a huge change. So they were able to use the same sort of system. So that's why architects were very happy with this solution as well.
Yeah. I think finally we're just going to look at the application process, which is critical to the design. Obviously, your design, if it's not applied correctly, you're going to have a problem.
Yeah, so for that very reason, the application is not subcontracted by us. We do it by ourselves, by the guys who are employed by us. So they all go on site once they've done the proper training and everything. And for that reason, we are like full service provider. We can do design, supply and install and everything. And as you said, that this is the most important part. You can design it as well as you want, but if it is not applied correctly, it will not work on site. So for that reason, it is done by our own guys only. So this is basically the application on a column or a vertical element, you can call it. So the first thing will be surface preparation, which is done by diamond grinding, followed on by cleaning. So they clean the area. They need to make it dust-free environment, because if there is any dust, it will affect the bond. After that, they do priming. Priming is done using pure epoxy. The reason for using pure epoxy is that so that it can soak into concrete and you get a better bond. Then they apply first coat of thickened epoxy, which is the white color epoxy you can see. And then they apply the first layer of carbon fiber. Now in most column strengthening cases, the application is generally done as confinement. So your primary direction of fiber will be in the hoop direction. So that's why they are wrapping it column, and that's why it's called column wrapping as well by some clients and contractors. So once they apply the first layer, they'll put another coat of epoxy, then they apply another layer. And that's how they build up the number of layers. Now the other thing to note here is that the carbon fiber these guys are applying is actually saturated in a different area on same site. So when they're applying it in this place, it is in wet condition. That's why this application is called wet layup method. There are still people out there who do dry layup. So in dry layup, what you do, you just prime the area with the epoxy, try and patch dry fiber with your hand and put another coat of epoxy on that dry fiber. Now in that case, nobody can guarantee the 100% resin impregnation through the fibers. And that dryness could lead to a debonding or delamination failure.
So how many layers are we able to apply in one day, one shift?
So yeah, in a vertical and vertical or overhead application, we can apply 3 layers in one day or one shift. After that, we'll have to leave it for initially set or cure, because if you just keep on applying further layers, the saturated weight might drag it down. So you'll lose the actual place where it was applied and everything. So for that reason, you're limited to 3 layers. Then you have to wait for it to initially set, which is usually in ambient condition is 4 to 6 hours. So it will be touch dry in 4 to 6 hours. So you can come back next day and apply further layers, and it will be 100% cured in 3 days time or in 72 hours, which means you can reload your structure back to its new capacity in 3 days time.
And just a key point is people ask the question about the finish, the type of finish, and fire protection.
Yeah, so after the carbon fiber is applied and it's cured, you can do anything on top of it. You can plaster, paint, render, you can do anything on top. In terms of fire protection, yes, carbon fiber can be fire protected if required. So you have to check it in design whether your carbon fiber need fire protection or not. If it does, then there are some additional systems or coatings available which can be applied on top of it. So there are all types of fire protection system. You've got an intumescent paint. You also have a cementitious fire protection system, and also some fireboards. So it's up to you what strategy or technique you want to use, but it can be fire protected.
That's great. Okay, and that's it. That's our presentation for today. If you have any questions, please drop us a line, drop us an email, and we will get back to you. So thanks from me today, Steve Musa, and from our technical director, Jayesh.
Thank you so much.
Thank you.